Welcome back, everybody. Here I'm going to talk now in this unit, this post-Thanksgiving unit, on gravity. So what I want to talk about right now is gravity in particular. What I'm going to call this is universal gravitation. I should mention, this isn't like my word. I didn't make up this phrase, universal gravitation. This is associated, again, with Newton. So this is back to our friend Newton. So he's working late 1600s, let's say 1665-ish. And there's this really famous story, which is a kind of a ridiculous story, the story of Newton. You must have heard this, where he's sitting under an apple tree and an apple falls and hits him on the head. And as the story goes, he realizes at that moment, and he's the first person to realize at that moment, that things fall, which is, of course, ridiculous. It's certainly people before Newton realized that objects on Earth fall to the ground. He wasn't the first person to realize that. It's this word universal that is interesting. This clues us into something, or one of the things that Newton figured out about gravity that people did not previously know. So I'm going to go over a few things, a few ways Newton contributed new information or new insight into our understanding of gravity. First, let's delve into this word universal. Universal means everywhere. It's universal. It applies to everything. And that is something that Newton realized. So in one sense, one little bullet point we could make is that Newton is the first person to realize that all objects that have mass, all objects, exert gravity. Okay. Prior to this insight, the common belief was that Earth was the only object that exerted gravity. And you can certainly understand why somebody might feel that way. In my everyday life, I am very aware of Earth's gravity. I am not at all aware of the gravity of another human being. I'm not aware of the gravity of a baseball. I'm not aware of the gravity of a passing car. I'm not aware of the gravity of the moon. I'm not aware of the gravity of the sun. I don't feel these gravitational pulls. I do, however, feel the gravitational pull of the Earth, however. So you can understand why somebody might be tempted to think that gravity is a property that's unique to Earth. But according to Newton's insight here is that, in fact, this is something that all objects possess. All objects that have mass exert gravity. And, of course, we do now know, it's common knowledge for you all, that Earth isn't the only thing that exerts gravity. Clearly we know that the moon exerts gravity. We know the sun exerts gravity. We know other planets and stars exert gravity. Maybe you didn't know that that all objects exert gravity. Maybe that is potentially news to you. You exert gravity on people around you. All right. Now, the reason you don't notice it is it's an incredibly tiny amount of force. The amount of force between you and another human being, that if you're in conversation with another human being and you're standing about a meter apart, the force between you is something like 1/1,000,000th of a Newton. It's a tiny amount of force, and so we don't usually notice it. But according to this concept of universal gravitation, all objects, including you and me, exert gravity. Another insight when he extended this is he said that the moon is affected by the Earth's gravity, that the moon falls essentially due to the Earth's gravity. And this was sort of a new idea, and that it was an interesting enough idea that I want to spend just a couple minutes and flesh it out. So the moon, I'm going to put this in parentheses or in quotes here, falls due to the Earth's gravity. And this is, again, an insight that Newton has, and it's interesting enough, again, that let's delve into it a little bit. What does he mean by the moon falls due to Earth's gravity? This is not at all clear. You don't think of the moon as falling, right? The moon goes around the Earth. It doesn't fall into the Earth, right? If I throw a baseball, the baseball clearly falls. It will fall into the Earth, but the moon doesn't do that. It never hits the Earth. So what is that all about? So the thought process is this, and I want to go over this a little bit. So here's the Earth. Let's say I just draw the surface of the Earth. So here's Earth. And let's imagine that I am standing on the Earth, and this is obviously not to scale. That's a very messy picture. Let's try that again. So here I am. and I'm standing on the earth, and I throw, let's say I throw a baseball. Okay, so I'm going to throw a baseball, and if I throw it out, I throw it straight out. I'm going to aim this way, straight out. That's where I'm aiming. I'm aiming completely horizontal. Well, what is that baseball going to do? Well, it's going to go out and it's going to fall into the earth like that. And if I throw a little bit harder, let's see if we can do this. If I throw a little bit harder, it's going to go a little bit farther, but it's going to fall into the earth again. And if I throw it a little bit harder, it's going to go farther, but fall into the earth again. But you can see what's happening here. As I throw it harder and harder, it goes farther and farther before falling. And you can see here that the curvature of the earth starts to come into play. So if I threw it even harder, it's going to go even farther, right? Before it hits the ground. You can see that it's clearly the curvature of the earth is starting to become important here. The harder I throw it, if I were able to throw it really, really hard, the harder I throw it, essentially the farther it falls. It has to fall a farther and farther distance, right? Because it's leaving from this height here. Try to do that again here. But these balls that are being thrown harder and harder are falling a greater and greater distance due to the curvature of the earth. And what Newton realized is if you threw this baseball hard enough, look what would happen. It would go so far that by the time it fell, it would have cleared the curvature of the earth. You can see this last line. By the time the ball has fallen far enough, it has cleared the curvature of the earth. And in this case, this object right here does not fall into the earth. In some senses, it falls around the earth or orbits the earth. And this is, according to Newton, Newton has the insight to see this is what's happening to the moon. The moon is indeed falling due to the Earth's gravity. But it happens to be moving fast enough that by the time it would fall into the Earth, it has already well cleared the curvature of the Earth. And so it continues to fall and fall and fall, and it indeed falls around the Earth and becomes a satellite. Satellite is an object that's orbiting, right? It's orbiting, it's going around the Earth. So according to Newton, the moon is a satellite. We now, of course, have satellites, man-made satellites that we know orbit the Earth, but the moon is essentially doing the same thing. Going so fast that rather than falling into the Earth, it effectively falls around the Earth. So this is a very famous insight that Newton has into the relationship between the Earth's gravity and the moon. Sort of interesting. Two contributions here to mention about Newton and gravity. All objects exert gravity, and then the moon falls due to the Earth's gravity. The last contribution I want to reference is Newton, sort of famous for trying to quantify science by trying to put equations and numbers to describe the science. So what he said is he wanted to know, how could I calculate the force of gravity? He wanted to calculate gravity. It wasn't enough to explain it, right? All objects exert gravity. Okay, well, that's well and good, but how would you find the force in newtons, the force between two objects? And I want to go quickly over this equation that he derives, and there's a really interesting derivation, a way he comes up with this equation that I'm not going to get into right now. But suffice to say, he determines that there's an equation, very simple equation, to determine the force of gravity. Okay, and I'm going to write this out. And he says it really only depends on three things. So if I have two objects, let's say here I have, that could be a star or a planet or a ball, it could be anything, but let's just call it M1. That's M1. And maybe I've got another object over here, another mass. It could be a planet, it could be a star, it could be another rock or a ball or something like that. And they're separated by some distance. There's a distance between them here. So if I take a look at the distance, and we're always going to measure distance from the center of one object to the center of the other. This distance here is called r. R is for radius, because gravity emanates out in a circle or in a sphere away from the center of an object. So that's why I'm using radius, r, rather than d for distance. I'm going to call it r. And he said that the only thing that matters here, the only relevant factors to figure out the force between these two objects is what's the size of M1, how massive is M1, what's the size of M2, how massive is M2, and then how far apart are they, r. So the three factors, and I'm going to leave a little space right here, so you might want to leave a little space in your notes. He says take m1, that mass in kilograms, multiply it by the mass in kilograms of m2, and then divide it by the distance between them, r squared. Again, I'm not going over this, but there's a reason he figures out all these relationships. So the only things that matter are the size in kilograms of m1, the mass in kilograms of m2, and the distance from the center of m1 to the center of m2, which is r squared. Okay, and then we can see what would happen. Let's imagine that each of these weighs a kilogram, and let's imagine the distance between them is 1 meter. What would you get? Well, you'd get 1 times 1 is 1, divided by 1 squared is 1, so you would get 1. This whole thing would be 1. If this were 1 and that were 1 and that were 1, you would get 1 Newton. This would imply that if you had two 1 kilogram masses that are a meter apart, there would be 1 Newton of force between them, which is obviously ridiculous. If you took two 1 kilogram masses, there would be no force between them. You'd never be able to feel the amount of force between them. It would be incredibly small. So there's another value that Newton knew had to be here. There was a constant that you'd have to multiply this whole thing by in order to get this to come out in terms of newtons. And that constant is big G. Big G this is an important constant, really important constant. This is the universal gravitational constant. Okay, it's the universal gravitational constant, big G. And if you know what that is, if you can figure out what big G is, now you can perform a calculation based on the mass in kilograms of m1, m2, and then the distance in meters r between them. You could figure out the force of gravity between any two objects in the universe. This is the idea. There we go. Problem is, we'd have to determine what is this value, and we're going to see, I'm going to show you in a minute that this isn't necessarily the easiest thing in the world to figure out, but I'm going to explain how you would determine the value of big G in just a minute. Before I do, I want to point out the fact that you're dividing by the distance between them squared. You have an r squared down here. This has a sort of famous name. This is called the inverse square law. Inverse square law, which basically means that the force of gravity is proportional to the inverse of the square of the distance. So as the distance gets bigger and bigger and bigger, the force of gravity gets smaller and smaller and smaller, but it isn't a linear relationship. The force is inversely proportional to the distance squared. So what does that mean? Well, let's think about it. If you suddenly got twice as far away from the center of the Earth, the force of gravity on you wouldn't be 2 times smaller, it would be 2 squared, or 4 times smaller. If you got 3 times farther away from the center of the Earth, the force of gravity wouldn't be 3 times smaller, it would be 3 squared, or 9 times smaller. Hopefully that gives you some intuition for this relationship between the force of gravity and the distance between the objects. It's an inverse square relationship. Hopefully that makes some sense. What I want to do now is think about this universal gravitational constant, because we need to know what this value, big G, is in order to use this equation. I'm going to show you how to use this equation, but I want to point out that Newton never knew the value of big G, which is kind of tragic when you think about it. He did all this work to come up with this equation that would allow you to calculate the force of gravity, but he could never actually use it because he never knew what big G was. It wasn't until much later that anybody knew what big G was, so I'm going to skip down here, and I've got a little picture here of a very famous experiment, which is associated with a guy named Cavendish. So this is the Cavendish experiment. Oh, go back to white here. This is the Cavendish experiment, which is very famous in physics circles. This is by a British guy by the name of Cavendish, and this is the late 17th or late 18th century, late 1700s, like 1798-ish, 1797, 1798, in and around there. So it's a bit of a ways after Newton when you think about it. So this is considerably after Newton. And what Cavendish wanted to do is he wanted to determine the value of big G. And actually the reason he was interested in this, it might be worth noting, is that what he was actually trying to do is he wanted to know what is the mass of the Earth. So if we go back, let me explain this. If we go back to Newton's equation here, let's say you want to know the mass of the Earth. How would you, right? We haven't even talked about how anyone might know the mass of the Earth. Well, I know my mass. I can determine my mass. Let's say I'm 70 kilograms. And if I know how far away I am from the center of the Earth, if I know the radius of the Earth, which actually can be determined relatively easily, you don't need to do any magical work to determine that. So if I know my mass, if I know the radius of the Earth, and I know the force of gravity on me, which I do, that's my weight, right? We've talked about weight quite a bit. If I know my weight, my mass, and the radius of the Earth, if I can figure out what big G is, I could calculate M2, which would be the mass of the Earth. And this is what Cavendish wanted to do. But to calculate the mass of the Earth, you first need to determine the value of big G. So determine big G. What is the value of big G? And essentially what he does is he realizes, getting back to this equation, that I can rewrite this equation right here to solve for big G. I could write that big G, go down a little bit here, if I rearrange this equation, I could say that big G equals the force of gravity times r squared divided by m1 times m2. Okay, I just rearranged this. I multiplied both sides by r squared, and I divided by m1 times m2 in order to isolate G. So he realizes this. Let me rewrite that down here. He says I could calculate big G by saying, if I can find them, if I say the force of gravity between two objects multiplied by the distance between them squared divided by their masses multiplied together, I could find big G. So he said, well, what if I just take two ordinary objects? Let's call them M1 and M2. Let's take an M1 and an M2. I could use any ordinary object. Maybe I take a ball of 6 kilograms and then another ball of 6 kilograms, and I put them a certain distance apart. Maybe I put them half a meter apart. Find the force between them, and I can calculate big G. No problem. Seems like it'd be an easy thing to do. The problem is that gravity, and I referenced this before, gravity is very, very weak force. It's extremely weak. So if I had two 6 kilogram masses, the force between them will be incredibly, incredibly small. And so small, in fact, that it'd be really, really difficult to measure this force. So the brilliance of the Cavendish experiment, and I have this cartoonish diagram of his apparatus that he used over here. The brilliance of this apparatus, and the reason it took so long for anybody to do this, is that he figured out a way to measure the minuscule, the teeny tiny forces between two everyday sized objects. So what he has here, and I'll see if I can write over this picture. I don't know if I can or not. Yeah, I can. Okay, so he says this ball, so let me back up. There's a rod, right, with two metal spheres on the end. And then this rod is hung by this fiber. This fiber is a very, very thin, delicate fiber. It's actually sometimes called a torsion fiber. It's a torsion fiber. And you can think it would be something like imagine a very, very fine fishing line. And this is balanced perfectly, this fiber right in the middle of this rod with these two equal masses on either end. So delicately balanced that the slightest push or pull on either end of this rod will cause the fiber to twist. And the way the fiber works is when it twists, if it twists, the more the force that's applied, the more the fiber will twist. So if you twist it hard, the fiber will twist a lot. It will turn a lot. If you were to twist it gently, it would only twist a little bit. So based on how much the fiber twists, that will tell you how hard you're pushing or pulling on the rod. Okay, and this you can get an appreciation in a minute for how carefully balanced this would have to be. So he's got this mass, M1, on the end of the rod, and he takes another mass, let's call it M2, and he brings it close to m1. So there's a distance here between these two. We'll call that distance r. And he knows these masses. I forget what the masses are that he used, but he took two masses, m1 and m2, that were kind of everyday sized objects. They weren't huge. They were normal metal spheres. And he brought them relatively close together through some distance r. So let's go back to the equation here. What does he know? He knows m1. He's got that. He knows m2. He's got that. And he knows how far apart they are. R. He's figured that out. So what he's got to do here is figure out the force of gravity between them. And this incredibly careful balance, this is essentially a fancy balance. In fact, sometimes it's called a torsion balance now. Torsion balance, I'll write that over here. This very, very careful balance will allow him to figure out the amount of force. There's going to be an attraction here, right? Very, very teeny, but there is going to be an attraction. This m1 is going to be pulled towards m2. It's going to be pulled that way. So this whole thing is going to twist, right? It's going to twist this way due to this attraction right here. The whole rig is going to twist, and it's going to turn right here through this angle, right? It's going to turn as this thing twists. It's going to turn. And using a light and a mirror, he was able to reflect this beam of light off of the mirror, and depending on this angle, we'll call that angle theta, depending on the angle that this fiber twists through, he can determine F. Okay, so the amount of twisting in this fiber allows him to determine F. And so he actually does this, and now he's able to figure out with this balance the force between these ordinary metal balls, M1 and M2, based on the distance between them, r. And he does this experiment very, very carefully in 1798. I could get more into the details of it because it's such an interesting experiment. I'm not going to go into all the details, but suffice to say, he had to find a way to do this in a room where there was absolutely no air. Right? He had to be in this chamber where there was no airflow, because the slightest little airflow, the slightest breeze would cause this incredibly delicate balance to twist and turn like crazy, because the slightest force on this balance would cause it to turn. So in order to make sure that the only relevant force was the force of gravity, he needed this to be in an area where there was no air, so that there could be no air currents in order to get this just right. And he did a pretty good job. He was able to determine a value of G that's pretty close to the accepted value, and we now know that G equals, end result, 6.67 times 10 to the negative 11th. This is the value of G. 6.67 times 10 to the negative 11th. He didn't get exactly that value, but he got a reasonably close approximation. I want to point out this is a really small number, right? Very, very small, 10 to the negative 11th. If we get back up here to this equation, this 6.67 times 10 to the negative 11th is very, very small. What does that mean? Well, it means what we already know. Gravity is a very weak force. So I'll write that out. Gravity is very weak. Okay. In fact, this is why we don't notice the gravity between people we're in conversation with, because the force is so puny that you're never even going to notice it. That's the reason for that. So that's the Cavendish experiment. A little bit of an explanation for how he did his experiment to determine G. What I want to do now is show you how you might use this final equation now to calculate the force between two objects. So let's imagine I could ask you, here's a question, determine the force of gravity between myself, Mr. Kerrigan, and the Earth. Okay, and here are our givens. What do we know? We know the mass of the Earth. I'm going to tell you that the mass of the Earth is equal to 6 times 10 to the 24th kilograms. By the way, this little notation here, this little plus sign with a circle, you might not be familiar with that, but this is the sort of the symbol that's used for Earth. So when I write that little subscript, the little plus, I mean Earth there. So the mass of the Earth is 6 times 10 to the 24th kilograms. My mass, so mass of Kerrigan, is equal to 70 kilograms, let's call it. And what else do we need to know? We need to know the radius of the Earth. What's the radius of the Earth? What's the distance between, if I'm on the surface of the Earth, what's the distance between me and the center of the Earth? And that value is something like 6.4 times 10 to the 6th meters. So here are our givens. And of course we've got the law of gravity. F gravity equals G times m1 times m2 over r squared. So let's call this, we'll say that this is m1. We'll call my mass m2, and of course here's r, and we know g now, right? G, we know, that's actually one of our givens as well. G is 6.67 times 10 to the negative 11th. So now I can go ahead, you can see here, it's with these givens, once I know the mass of the Earth, which is a well-known constant, my mass is 70 kilograms, the radius of the Earth, a well-known constant, and now I've shown you how to find G. We can just plug these values into Newton's equation and determine the force of gravity between me and the Earth. So let's do it. I can say, alright, so this is going to be equal to the force between me and the Earth. It's going to be 6.67 times 10 to the negative 11th. What did I call m1? That's the mass of the Earth. That's 6 times 10 to the 24th times my mass, m2, is 70. Divided by the radius of the Earth, that's here, 6.4 times 10 to the 6th squared. So I know all the values. Now I just have to calculate this out. And you can see now maybe why I spent a little bit of time going over the scientific notation. I've got a really small number here, a really big number here. It's helpful to have scientific notation in order to write out this equation. And so now I'm going to calculate it out. I have here the handy graphing calculator. So I'm going to go ahead and try to calculate this out. I'm going to say, if I can, there we go, turn this on. I'm going to say, all right, 6.67. Now I remember I need to get that E. I need to get that our way of using the calculator to express scientific notation is by using that E, which I access by hitting second, and the comma gives me the E. Now negative 11th, remember you don't want to hit the minus sign, you want to hit the negative sign. Negative 11 times mass of the Earth, 6, E, 24, times, what's my mass? 70. Okay, so I've just plugged in, that's the numerator, the three values of the numerator, divided by 6.4 E, 6, and then square that. Notice I don't have to, I didn't have to put parentheses here, right? I didn't have to put parentheses around the 6.4 times 10 to the 6th. Again, the calculator will read this as one number. It won't square the 6 and then raise 6.4 to that value. It will recognize this as one number and square it appropriately. So hit enter, and what do we have here? There we go. Yes, this makes sense. So what did I end up getting here? I got 684 newtons as my answer. Answer is, back here, 684 newtons. That's the force of gravity between me and the Earth, about 684 newtons. By the way we used to, this is the force of gravity between me and the Earth, right? This is what we used to call this the weight. This is my weight. We used to calculate this mg. Let's see if we get a similar value if I did mg. What if I did our old mg, 70 times 9.8? 70 times 9.8. And what do we get? We get 686. So it's very, very similar value. Again, what we used to do is say weight was mg, and mg, if I do that out, I get 686. So slightly different, just rounding difference, but you can see you end up getting the same value regardless of whether or not you used mg or if you used Newton's gravitational equation. All right, hopefully that's a helpful introduction to what gravity is all about, and an example of how to use the graphing calculator to do these calculations. We will practice calculations like this in class next time. See you then.